Okay, welcome to another session of process control system, and today we are going to look at Ziegler-Nichols controller tuning, or determining the controller settings or the adjustment of the controller gains. So the use of proportional control usually require just maybe one variable, because we know that when you talk of the controller, or when you talk of the proportional control, there will only be one variable, and that is Kp for proportional. That is the gain for proportional. For the control system to have the required dynamic behavior, the use of Pi, that is proportional plus integral, usually require the selection of two variables, that is the Kp and the Ki. That is Kp, the constant for proportional, and Ki, the constant for integral. And when you talk of the PID controller, then we usually have three variables. That is the Ki for the integral, Kd for the derivative, and Kp for the proportional. And this selection of the variables usually enable the locations of the enables the locations of the poles and zeros to be introduced by the controller, and then hence to be determined, and this one will always affect the offset of the stability control system. And in this case, when you talk about the term tuning is always used to describe the process of selecting the best controller settings. And there are a number of methods that are always used, but in this case we are only going to look at two, of which the two methods that we are going to look at, one of them is always referred to as the process reaction curve. So both the two methods were designed by Ziegler-Nichols, and that is why we referred in the topic we were talking about the Ziegler-Nichols controller tuning. So the two were designed by Ziegler-Nichols, and both methods are always based on experiment and analysis of the systems that are used frequently. So the first method that we're going to talk about will be process reaction curve. Process reaction curve. And then the second one is ultimate cycle method. Ultimate cycle method. Ultimate cycle method. So we are going to start by looking at the process reaction curve. When you talk of the process reaction curve, maybe we can use a block diagram in order to illustrate what is going to happen. So when you talk of the process reaction curve, just by using the normal control system, a block diagram like that. Here we have the controller. Here we have the actuator. Here we have the process or plant. Then of course we have the output. Then there is the feedback there that goes through the sensor, or rather the measuring means. So in this case we have the reference input R, the error, and then here we have the feedback, that is B. Then this is the measured signal. Measured signal. Measured signal. And then this is the output C. So when you talk about the process reaction curve, then in this method, we usually open up the control loop. So we open up the control loop at this point. So this point, we open it up, and then we feed a small test signal through that. So here we have small test signal. We feed small test signal through that. And in this case, this break is always created. A break will be created between the controller and the actuator, as illustrated in the diagram. Then a small test signal is induced. A small test signal will be induced in the actuator or the final control element, and the resulting measured signal is plotted on a graph over a given time. And this one can be illustrated as shown in this diagram. So we are going to see how we are going to so we have the diagram here for the test signal in terms of percentage. So this test signal in percentage, Then from there, we can have some given value P, So you have some given value P here. Of course, that is against time. You can have some given value P. Then this is now the test signal that was injected in the actuator. Then we can have the corresponding measured signal also in percentage. The corresponding measured signal in percentage. We have measured signal M going in that manner. Then at this point, we can have a sigmoid, almost S-shape, in that manner. Then we can assume that, assuming that the gradient, we have a straight line. Then from there, we have value of L. This is called L, which is the lag. Then here we can have T. Then from here, we can have the measured signal. And of course, both of them are in percentage. Then this one is also against time. So that is an illustration of a process reaction curve. And this process here, when you have that, we say that we can use this particular graph in order to determine the value of the best values for the controller's tuning, the best constant values that we can use in this case. So when we use this method, as we have said, the procedure is always to open the control loop so that no control action that occurs. And generally, this one is always made at the actuator. And when you make it at the actuator, which at times we refer to as the correction unit, and then a response will be measured. A response of the measured process variable will now be determined. That is what we are going to look at is we are going to determine that is the error signal. The test signal should be as small as possible, and the figures that we've just shown on that can be used in order to get these values. So the test signal is what we're referring to as P from the graph. We refer to it as P, so P is here. We refer to the test signal as P, and the measured variable is expressed as a percentage of the full range. Then with that, a tangent will be drawn. A tangent will be drawn to give the maximum gradient of the graph, and that is where the straight line is. A tangent will be drawn that just touches that curve at one point to give the maximum gradient of the graph as shown in that particular figure. And then for us to obtain the maximum gradient of this will be obtained by, so we can say the maximum gradient R will be obtained by getting the change in Y all over change in X, of which, if we look at this, our change in Y in this case will be M all over T. M, which is here, all over T, which is the maximum gradient. So we are only taking at where it is tangential and where it is cutting that particular point. So that is what we refer to as the maximum gradient. The time between when the test signal started and when this tangent appears on the graph is always referred to as the L, that is the lag time. And you can see it from that, so that is the lag time. And from there, we can always use those values in order to determine the best controller setting. So it is this criteria that was recommended by Ziegler and Nichols for the controller settings, and this is always based on the values of P, R, and L. So there are empirical formulas that were used by the Ziegler-Nichols, as we will give in this table. So we are going to give the empirical formulas that we are used, that are to be used in order to get the preferred or the best controller settings. So here we can have the control mode. Then we can have the control mode. So after the control mode, we can have, here we can have, if it is only proportional only, then we can talk of proportional plus integral. Then we can have proportional plus integral plus derivative, which we are referring to as the PID. So here we can have the various constants, that is the Kp, Ki, and Kd. So PID, so these are the values that we can have. When we only have the proportional, then the value for Kp will always be given by P all over RL. And of course, in that case, that one will not be existing. There is nothing for integral and there is nothing for the derivative. When you come to the proportional plus integral, then the value for Kp will be given by 0.9 P all over RL. And for the integral, it will be given by 1 all over 3.33 L. And then, of course, because we only have the proportional plus integral, we will not have the value for the Kd, that is for the derivative. Then we can talk of the Kp when we have all those. Then this one will be given by 1.2 P R, 1.2 P all over RL. Then here 1 over 2L, and then here we'll have 0.5 L. So those ones are the empirical formulas that you can use in order to determine the values of the controller settings or adjusting to get the best control by use of the process reaction curve. So the other method that is also still was carried out by Ziegler and Nichols is what we refer to as the ultimate cycle method. The ultimate cycle method. In this method, first the integral, in this method of Ziegler-Nichols controller tuning, in this method we find that the integral, the derivative, actions will be reduced to the minimum values. You first of all have to reduce them to the minimum values. Then the proportional constants Kp will always be set and then gradually increased. Then after this, what we are simply saying is that the proportional band will always be made to be gradually narrower. While doing this, small disturbances are applied to the system, and this is continued until a continuous oscillations occur. So after the continuous oscillations have occurred, then there will be, after we have had the continuous oscillations that we are talking about here, then the critical value of the proportional constant that we usually refer to as Kpc, that is the critical value. Kp simply means the constant for proportional, and then C means that that is the critical value at which these particular oscillations occur will be noted, and the periodic time of the oscillation, Tc will also be measured. So we can always use this table in order to determine the Ziegler-Nichols as recommended criteria for the controller settings. So we can have this value. So in this case, we can have the controller mode. Have controller mode. Then we have proportional alone or proportional only. Then we have proportional plus integral, and proportional plus integral plus derivative. And in this case, we can talk of Kp, and we can talk of Ki, and we can talk of Kd. So in that case, when we only have proportional alone, then this one will be given as 0.5 Kpc, and of course that one will not be there, that one will not be there. P plus I, in this case, we will have 0.45 kpc, and then, of course, this one will be 1.2 t, should be 1.2 divided by tc, and then, of course, because it is proportional plus integral, we don't have the derivative, and then lastly, on this point, we are going to have 0.6 kpc, and also 2.0 or 2 all over tc, and then we have what we call 8 all over tc. So those are the values that you will be able to obtain. How you are going to obtain the values of the various constants as far as the ultimate cycle method is concerned. So the same presentation for both ultimate cycle method and the process reaction curve method can still be given indifferently, because we know in one case we will be using time, and another case we can always be using the frequency, and in that case you can always make a reference. There are some notes, there is materials that you will find at the website EES.education, and that one will enable you to find major references and maybe the differences when we use the frequency in order to come up with the values of the settings, or when we use the time in order to come up with the values of the setting. So another device that is always used in process control that we are going to talk about now is the actuator. We can talk of the actuators. So what is the purpose of the actuator, or what is an actuator? In most cases, when you have a control system, just by reminder of the block diagram again, then we have talked of this point where we have the controller. I think that is now what we had just concluded on. And then we've talked about what the actuators are. That is what we are going to talk about now. And then we have the process or the plant. So that is from the conventional block diagram of a control system. So here we have the sensor that is in the feedback that is always used in order to convert so that we have the input to be in the same level and the same dimension as the output. So when you talk about that, then what we are talking about is now the actuators. What is the purpose of the actuators? Just as we had mentioned earlier, then the main work of the controller is always to amplify the error. And this one is always done, and the output is always in terms of voltage. When we have a physical quantity as the input, then we'll have it to be changed to the voltage in the controller. So in this case, there is always an input transducer that is going to change that. Then we have the voltages at this point. Then when the measuring means, that is the sensor, will always convert whatever voltages that are here into a physical quantity so that the comparison is made. So that is why we say that it is converting it, it is making it to be in the same level and the same dimension as the input. When that one happens, then the difference will be amplified by the use of the controller. And the main work of the actuator is always, the actuator always converts power into motion. It's supposed to convert power into motion. So when the actuator converts the power into motion, this is now what is going to bring about the movement of, maybe we can talk of the movement or opening or closing of a valve. The valve will open. Mostly when you talk of the actuators, we are talking about what will change the power that we had into the controller, into a motion that is going to bring about the corrective mechanism movement, so that if maybe it was a case of some control system mechanism is supposed to be implemented, then that one will actually reduce. We either reduce depending on the sign of the error, whether it is positive or negative. So that is what actuator is always about. It is always very, very necessary in a system in order to move large mass This one can be through an angle or on a linear distance. And in order to be able to do this form of actuator, a form of actuator will be required. And an actuator usually require, there are two major requirements that an actuator must have. The first requirement that an actuator should have is that an actuator should be able to produce sufficient power. So the first requirement is that, so maybe we can talk about the main requirements of actuator. Requirements of an actuator. So when you talk about the requirements of an actuator, then we have said that one requirement of an actuator is that it must be able to produce sufficient power. So must produce sufficient power. So it must produce sufficient power. The other requirement is that it must be controllable. Must be controllable. It must be controllable. And when you talk about the actuator, one form of an actuator is simply, you can talk of a simple DC motor, which is attached to a suitable gearbox, such that the angular velocity of the output is smaller than that of the input. And if it is for an angular movement of large mass, is what is needed, then the direction and speed of the motor has to be controlled. And this is always achieved by using a DC motor with a separate field winding. And the field is always energized by a steady current that is passing through a varying, that will pass through a varying direct current, that is the DC, through armature that is passing through, you'll have it must pass through a varying direct current through armature that enables the speed of the armature to be governed. And reversing the direction of the armature will always reverse the direction of the rotation. So in that case, that is what actuator is all about. So let's talk about, very, very briefly, we can talk about the several types of actuators just by a mention. So for more materials, you can go to the website, EES.education, if you want to get more materials as far as the actuators are concerned. So when you talk about the actuators, the several actuators that we can talk about, one of them is what we can refer to as the solenoids. The solenoids. So when you talk about the solenoids, then this is just an electromagnetic device that we know that when you have some connection like that, and then you move something in between, and a ferromagnetic material in between, then of course there will be a movement. So it is this movement that we can always build up in order to come up with a certain actuator, because what we've said is that the actuator is just supposed to change power into motion. So there are several actuators that we talk about. One of them that we've talked about is the solenoids. So I've talked about solenoids. The other form of actuator that we can talk about is pneumatic actuators. Pneumatic actuators. So pneumatic actuators are always used in order to bring about movement, and the pneumatic actuators usually use the compressed air or compressed, we can talk of compressed air in order to bring about movement. So as the area changes, we know of the pressure is equals to force over area. So as the area changes, as we force it, there will be pressure that is built up from that. So you will have something like a cylinder like that. Then of course you have that. So when the movement goes back and forth, then it changes the pressure, and at times the air will be released, and that one will result into a movement. The other type of actuators that maybe before we can do that, we can look at what is it that this particular actuators, that is the pneumatic actuators, comprise of. One of them is the motor section, which comprises of a diaphragm whose position is set by the balance between the force exerted by the spring and the controller output pressure on the diaphragm. The other thing that it must also have is the valve, which varies the area through which the flowing fluid must pass. So that one is it's just a summary of what the pneumatic actuators are. We can also talk about the hydraulic actuator. This is a device which, so the third one, we can talk about hydraulic actuators. We can also briefly talk about hydraulic actuators. Hydraulic actuators. So when you talk about the hydraulic actuators, this is a device which amplifies a linear mechanical motion into mechanical motion at a much higher level. In general, they are always economical and usually provide a high power output per unit volume ratio. So this device usually uses a relatively non-compressible fluid, such as oil, in order to transmit power through the section of the fluid. So that is how it works. So as opposed to what we had in the pneumatic actuators, where we were using the compressed air, the main difference between the pneumatic and the hydraulic is that when you come to hydraulic, now we use a compressed oil in order to achieve the movement. One major disadvantage that we'll have in terms of hydraulic is that it will not give a clean environment. There will be oil spills all over, and that is one of the major disadvantages. And these particular types of actuators, they can either be rotary or they can be linear. So you can either have hydraulic that is rotary, arranged in a rotary form whereby it moves, the movement is circular form, or you can also have the pneumatic that is also either linear or circular, move in a rotary form. Of course, under that we can still talk about the rotary actuators. Of course, the rotary actuators, the main difference is now how they are supposed to move. Another one can also be a servo motor. We can also talk of servo motor. We can also talk about the servo motor. Number 4, we can talk about the split feed servo motor. Servo motor. Or again, we can talk about another one, which is what we refer to as the AC servo motors. AC servo motors. So these are simply the types of actuators that we can mention. So if you want more materials as far as the actuators are concerned, the diagrams and also explanation on each and every actuator and how it works, then you can always look at the materials at EEES.education. So the material is available at that particular website. So ensure that you look at that in order to get more information as far as the actuators are concerned. So another actuator that we can also mention is stepper motor. Stepper motors. So stepper motors, or rather what usually referred to as stepping motor, is a motor that usually produces rotation through equal angles. And that is why it is always termed as steps. Through equal angles, and that is what we usually refer to as steps. For each digital pulse that is supplied, then if we have one input pulse, then one input pulse usually produces a rotation. And this rotation is it is always through what we call one step angle. For example, if we have a stepper motor that has got a step angle of, let's say, 36 degrees, then to make us one revolution, which is 360 degrees, then it means that to achieve that, then it will be 10 steps. We'll have 10 steps. So it means that when it moves, when a pulse is received, then it will move once through an angle of 36 degrees. And to obtain a complete revolution of 360, therefore we will need 10 steps. You can also talk about a stepper motor that has got maybe a stepping angle of, let's say, 1.8 degrees. That has got that one. For us to get 360, we are going to obtain how many steps? 200 steps in order to obtain 360 degrees. And this motor, this particular type of motor, can therefore be used for accurate angular positioning, and it is always used to drive continuous belt. You can always have it. It can be used to give accurate linear positioning, and depending on how you use it, you can still use it. You can also make it to be angular, both angular and linear positioning. So when you talk of the stepper motor, then in this case, the stepper motor, maybe an illustration on how it works. You have the motor here. You have the motor there. Then, of course, you can have the digital pulses. You have digital pulses. You have digital pulses. Then the output here will actually be the rotation in equal angle steps. Rotation in equal angle steps. The rotation will be in equal angle steps and 1 step per pulse. That one will be 1 step per pulse. And this one can always occur. Maybe if you talk of the linear positioning, you can have that. Maybe you can talk of a pulley wheel here. Then now you have your object. You can have your object placed here for linear movement or linear positioning. So this is what we refer to as the stepping motor, how it will work. And then for the linear positioning, you can have that. Maybe you can have an object that is positioned in that point. So you have an object, it can either move in any direction. So this is the object positioned. It's an object that is positioned. Then here we have the pulley wheel. And here we can have a motor. So that is how it works. So in this case, we are simply saying that whenever one pulse is, whenever it receives a pulse, it moves 1 step angle until it will be able to carry out, it will be able to revolve 360 degrees. And when it stops, then a particular process or a particular function or a particular activity can be done at that particular point. And that is why we are referring to it as, that is why we are referring to this stepper motor as a digital motor that can be used for linear positioning. Maybe I can add something. So if you need more more materials as far as stepper motors are concerned, there are some definitions and maybe a little bit of calculation on stepper motors, then you can all refer to the website EEES.education. So at that point, at that particular place, you will be able to find several materials as far as stepper motors are concerned.